All right, everyone. Thank you for coming today, especially on such short notice with the time change, the date change, and everything. So I appreciate you guys making it out today. Today I'm going to be talking a little bit about the apply family of functions in R. I'm going to motivate where this came from a little bit, where the idea for this talk came from. In just a moment. I also want to say that I've really enjoyed leading SLG this semester, so I thank you guys for your participation. One of the things that I've really enjoyed about working with SLG is that we have such a broad range of topics that we can cover. So at the beginning of the semester, we looked at all of our traditional machine learning problems and sort of went back to our roots and sort of saw where that led us. And we got to look at a different programming language in Julia for a couple of weeks. We also got to examine from a student request the philosophy of information and sort of some of the headier ideas from all of this that I thought were really intriguing. Also looked at Bayesian optimization. Then today's talk comes from a student suggestion as well. So it's neat to see that we can talk about all sorts of different things in this group. A lot of different things are really relevant. And so I'm hoping that the way that this applies, if you will, to machine learning is that this will help make your code more efficient. I imagine that a lot of you have seen the apply family of functions before. Maybe you've used it before. So I'm hoping to give you a very broad overview of all the different types of functions that say apply or letter apply. So let's talk a little bit about our motivation for this presentation first. Then I'll also discuss why R is a slow language. It sort of complements what we learned earlier in the semester together about how Julia is a faster language. I'll talk a little bit about for loops in R, why they're not the best idea, and also when they're the only idea that we have, unfortunately. We'll also talk about a brief introduction to these apply functions. I'll go through an R Markdown file that uses all the different types that we have. And then, so that'll be our implementation, and then we'll have our conclusion for the semester, and that'll be our time together with SLG until January. So our motivation for this talk, in the talk that we had on the 20th, our own Dr. Post used the apply function in his regression tree code, and of course that's all online in case you are interested in that topic. We had a student at that talk ask what the difference was between apply, and I believe he asked about sapply, although I can't quite remember which one he asked about. And as I was sitting there, I said, you know, this actually wouldn't be a bad idea for an SLG talk on its own. I think that there are a whole bunch of apply functions. I'm not exactly sure what the difference is between them. It'd be nice to at least be familiar with it, not have to claw through all the documentation by myself. This idea sort of came into a broader view when on the 11th of October, Josh Day talked with us about why Julia is fast. And of course, the reason that we're going to talk about this apply family of functions relates to why R is slow. So it sort of tied in a bunch of different ideas from the semester. And I saw this as a great idea for a potential talk with SLG. And of course, if you've been receiving my emails this semester, it's always been down there as a suggested topic to talk about because I thought that it would be a great talk. And I was really hoping that somebody would choose to research it and give it. And then finally, a little bit later that month, Dr. Rich gave us a data challenge in the spatial statistics course. And I came across the need to use the apply function. And at the beginning of my code, I started to use the wrong apply function, and it was throwing errors back at me, and I was frustrated, and I said, well, somebody was supposed to give that talk at SLG, so that I could know how to do this. And so it was only moments later when I had the epiphany, all right, clearly I need to give this talk. I need to be doing this research. So I actually feel so much better about the apply family of functions after looking at this. I hope that you will today as well, and I would continue to ask people to speak with us today, to speak with SLG, because I believe that giving a talk really does enhance your view of whatever it is that you're talking about. And so I certainly feel so much more comfortable with the apply family of functions. I look forward to speaking with you today about them. So This slide here was actually pulled directly from Josh Day's slides. You'll recognize the Advanced R website. So this is Hadley Wickham's Advanced R text as it's listed on the website. If you go to the performance section in that text, the first bold header that you see under the title of the section is "Why is R slow?" I don't know, it's interesting that, so it's an advanced R book, right? And it sort of strikes me as interesting. I would really want to be a salesman for R if I was writing this book. So the very first sentence that's up there, so this is going down to that first section. You can see how long that description is. Some of the things that you can't see from a distance, these are links that come out of this part of the website. And it's very, very interesting to me. I would want to be selling R, naming all of its high points. And here in the performance section, we have all these links coming out of why it's slow. The very first sentence, I actually put right here on the slide, R is not a fast language. I know it does say at the end, this is not an accident. So this is an important thing to say as well. But at the end of the day, I thought that it was interesting. But just that, why would we want to say these things? And so let's develop a simple answer for why R is slow. Really, R isn't designed for the computer to do things quickly. R is designed for you to do things easily. So R is designed with you in mind. It's not designed with the computer in mind. In fact, in those paragraphs that I showed you, one of the most important quotes that I saw, Hadley Wickham says, "For most purposes, it's fast enough." And I believe that that rings true. One of the best examples that I saw as I was researching for this presentation, when you type something like A equals 3.00, so you assign the value 3.00 to A in R. That's what you type. But maybe the better thing to think about why R is slow is to answer the question, what don't you type? So what are the things that you're not telling R when you simply assign this value 3 to the letter A? Well, first of all, you're not telling R that 3.00 is a floating point number. R is asking itself that question and inferring based on what you type that that is indeed a floating point number. Another thing is that this A that you have is going to store data. That's what the arrow indicates. And that data that it's storing, this 3.00, is of type numeric. So of course, types in R, you could give it your own lecture on that. So I'd encourage you to look at that if you're interested in all the different types that R provides. This 3.00 that we have, where R is inferring, because we need that, because we've made an assignment, that it needs to be stored in memory. And moreover with that, when we type the letter A, we want A to be the pointer to that place in memory. So again, these are some of the things that you're not typing, right? That R is trying to infer. And one other thing, again, this when I asked myself this, I said, well, 3.00, so 3 in binary, looks to our eyes like the number 11 to our base 10 eyes. Of course, that's not what it means at all. It means 1 copy of 2 to the first power plus 1 copy of 2 to the 0 power, 2 plus 1 being 3. But that's not the only thing that's important here. So 3.00 equals in base 2, and here are all of our 8-bit strings. So here's that 0011 I just mentioned earlier. This is probably what I could do by myself. Of course, I could also tell you that 0000 and 0000 are these two zeros out here. Before this presentation, I could not have called to you that this is the byte string for a decimal point. So again, you don't have to tell R that that's the number that you're referring to. It will do that for you. So again, just some, what are we motivating here? We're asking ourselves, what don't you type when you make an assignment in R? So this is just a brief list of things that R is doing for you. So here's a start to a more technical answer to the question, why is R slow? R is a high-level, what we call interpreted computer language. For example, the other type that you see often, programs like C and Fortran, these much faster languages, they're called compiled computer languages. These interpreted languages like R answer each one of these questions like I referred to on the other slide. if it's a floating point number, how we're going to store the data, if we need to store the data, what its pointer is, all those sorts of things. They're going to ask themselves each of those questions one at a time as they come. Remember, it's designed for you, it's not designed for the computer. So you don't have to do all this, but somebody does, and R is choosing to do all that for itself one at a time, right? These compiled languages like C and Fortran, they begin figuring out the answers to these questions immediately as you're typing. And you can help them actually by answering some of these questions for them. Perhaps you want to inform them that this A is going to store a floating point number, so it doesn't have to do that work for you. But R is not going to ask you to do that necessarily. One thing that Josh taught us back on October 11th is that Julia is a compiled language. So Julia is trying to do some of this in the background. You remember, just to give his talk the credence that it deserves, I do also want to mention, you remember he talked about that just-in-time execution, and it gives Julia that feel of an interpreted language. So he talked about how if you come from an interpreted language, but you want to move toward a compiled language for speed purposes, that Julia is a great program for you. So again, just to make sure that Josh knows that I listened to his talk, and I'm advertising his program that he loves. That's at least the beginning to a more technical answer. If you want to see more things about interpreted and compiled languages, certainly there's some more about it in Advanced R, but you can look that up on the internet in many different places, in many texts. I want to move on to talking about for loops specifically. Since we've talked about an interpreted language, let's talk about what for loops look like in an interpreted language. For loops, of course, we know that they're very simple and they're very intuitive. So you got some variable, and you want to say perhaps that going down each element of this vector, we want to do this thing. But in an interpreted language, this is a very clunky way to go about it. Now, why is that? Well, we just said that in an interpreted language, R doesn't force you to answer certain questions. It's always going to try to answer those questions by itself. It's designed for you. It's not designed for the computer. So R has to ask itself those questions that I listed every single time. Again, I listed out very clearly every single time. So as you're going down that n vector, particularly if n is large, in that big data setting that we talk about, imagine R having to answer each one of these questions n times when n is very big. That becomes very, very cumbersome in a computer language. Another thing to consider is that mistakes are very, very easy to make with all of this. One of the mistakes is probably the most common is a whole other point that I listed onto itself. Let's say that you've defined your for loop for I equals 1 to n, whatever your n is. That I is floating around somewhere in your workspace. And if you've got another loop coming up for I equals 1 to n, sometimes just because you've moved on from it, but your workspace hasn't, I can be saved as maybe something other than 1 and start to cause some real problems in your code. So this is something that we have to be very careful of. I encountered this problem a couple of years ago and just could not figure it out. So I had to clean up my workspace and start over. Researching for this talk reminded me of that time. So in spite of this, there are times when we need to forge ahead. Made a little joke there. So anyway, there are some times when we have to use a for loop, even if we don't really want to. For example, what about a time when each iteration depends on the previous one? Suppose you were wanting to write an R program that computed Fibonacci numbers for you. So you've got something that's recursive, and each iteration depends on the previous one, or perhaps the two previous ones in the case I just listed. That's something that doing something other than a for loop, it can be quite tricky. There are ways to do it. I saw a bit of code online as I was researching this that worked with a Brownian motion problem, and they found a way to avoid a for loop in it, but it required something very creative, required knowing that it was advanced computer science is what it was to avoid that for loop. So this becomes very, very tricky without some higher level knowledge. Also, if you're working with maybe a base function in R, something that you didn't build yourself, or maybe you're working with a function in a package that someone else created. Perhaps the functions that they wrote won't accept a vector argument. You have to take it one by one down each element of the vector. So this does happen sometimes. But so again, it's good to know how to do a for loop. You just don't want to do it in R, because R is an interpreted language. So what are some workarounds to these for loops? For example, we could use an if-else statement. If a certain criteria is fulfilled, you want to do one thing. If it's not fulfilled, you want to do another thing. So that in 3 arguments takes care of that without a clunky I that's in there perhaps. Maybe you avoid some of those mistakes. Perhaps still could be slow in a big data setting. And of course today we're motivating the apply family of functions, which is really going to help answer this question very efficiently. One thing to think about here is ultimately, as we're traveling down this vector, somebody's got to travel down it. There needs to be a for loop at some point. At some point you've got to go down and work with each one of these elements. So doesn't something have to loop? Well, yes, but who said that the interpreted language is the one that has to do the looping? So what the apply family of functions does is it hands off this task from R to C. So like we've talked about with C, it is a compiled language and not an interpreted language. So this can be done more quickly when we pass it onto a different place. So this is a very intelligent workaround for this. So what we're doing is I think about it almost like the quarterback is R. The quarterback is reading the defense and determining that perhaps it's that it needs to do something, that a pass is not going to work in that situation, so it is going to hand it off to the running back, who is C. In that particular play, it sees that there's an advantage to handing it off to C. So that's what the apply family of functions is going to do for us. I'd like to motivate the apply family of functions with one more brief introduction to a topic called functional programming. If you want to look more about this, I mentioned the procedure section in Hadley-Wickham's Advanced R book. There's a whole section on functional programming. And the reason for that is because, as Hadley-Wickham says, R is at its heart a functional programming language. So I just want to introduce what functional programming is, but not go too deeply into it. Essentially what R is it's a giant toolbox that allows you to create functions, allows you to manipulate those functions. So a question that you might ask yourself is, a lot of times you think about accepting a vector as an argument to a function. Well, why not accept a function as an argument to a function? Let functions act on other functions. And that's exactly what R does for us in a very clean way. These functions that act on functions are called functionals. In fact, at this point where he defines functionals in Advanced R, Hadley-Wickham goes on to introduce a function in the apply family called lapply. And you think about those baby books from when you were younger. You know, you've got maybe a picture of my first blanket or my first teddy bear, or a picture of my first step or something like that. He refers to lapply as my first functional. So I think as you're growing up in your programming life, lapply is something that Hadley-Wickham points out as something that's going to be extremely important to you.